Okay, for this lesson, we're going to be taking a look at a topic that seems strange to start, but it becomes increasingly common as you continue with math, and that is the idea of these things called special triangles. So what makes them special to start? And also the importance of exact values. Math teachers, mathematicians, I'm sure from a student's perspective we seem obsessed with exact values at times, but exact values are actually really important. It means that you haven't used your calculator, which means you haven't lost any precision in your answer, and that's a really important thing to do as you are doing certain types of math. Now, in the case of trigonometry and special triangles are going to involve these angles. So these are the acute angles that could be involved. And then, of course, the 90 degrees is the right angle. So that's your typical right angle triangle, could involve 90 degrees. And then any multiples of these things as well. So we'll be interested not just in 90 degrees, but 180 and 270 and 360. And for 30 degrees, 45 degrees, and 60 degrees, we're also going to be interested in those particular angles in the different quadrants, which I hope to illustrate to you as I work through this lesson. So the way that we're going to start is we're going to start off with a square of side length 1. Okay, so a square, it has 90 degrees in each corner, and I'm sure I don't need to write that part. And each of the sides is length 1. Now I've chosen a length 1 for a very specific reason, which you'll see in a moment. Now in this case, what happens if I divide this square in two? So if I draw a diagonal line from corner to corner. Well, if I do that, what have I done to this 90-degree angle? Since the square has all equal sides and all equal angles, that means that what I've done is I've broken this into two 45-degree angles. And it turns out that I've done the same thing up here, that these are also 45-degree angles. So now I'm going to look at the triangles that I formed, and in particular only one of these triangles. So let's choose the one that's in the bottom right. So that would mean that this, as I labeled before, that's 45 degrees, that's 45 degrees. This side is length 1, this side is length 1. Now what about this? What about this side? That we would normally label as, we could label that as any variable, but since that's the hypotenuse, so I'm going to label this side h. And so now I can say that h squared is equal to 1 squared plus 1 squared, which of course is h squared is equal to 2. H itself must then be equal to plus or minus the square root of 2, but h is a distance, so that means that h must be greater than 0, and so we end up with h is equal to the square root of 2. So now I end up with the triangle dimensions. It's got, well, this side is 1, this side is 1, and h over here is equal to the square root of 2. Now, knowing this, I can actually make some statements about the sine and cosine and tangent, in this case of 45 degrees. We're not talking about the 90-degree angle yet. So I can actually now say that the sine of 45 degrees is equal to, sine is opposite over hypotenuse. That's going to be 1 over the square root of 2. Cosine of 45 degrees is equal to adjacent over hypotenuse. That's 1 over the square root of 2. And the tangent of 45 degrees is equal to opposite over adjacent, which is 1 over 1. And of course, this one's the easiest one to simplify, which is, it is simply 1. For the others, let me just move this over and give myself a little bit more room. I don't think it's going to let me. No, it's not going to let me. Okay, that's all right. We don't like to have radicals in the denominator. And so to get rid of radicals in the denominator, we go through a process called rationalization. And what that, in the case of simple radicals like this, it just means I'm going to multiply the numerator and denominator by square root of 2. What effect does this have? 1 times the square root of 2 is just the square root of 2. But root 2 times root 2 is actually root 4. And of course that simplifies to root 2 divided by 2. Sine 45 degrees is root 2 over 2. I could have done the same thing with cosine. So the cosine of 45 degrees is equal to root 2 over 2. And as I had before, the tan of 45 degrees is equal to 1. Notice that all of these values are exact values. I didn't have to use a calculator to do these things, and I can represent these. I've lost no precision due to rounding from a calculated answer. So these are special angles, in part because they have these exact values that are completely consistent, and they do come up a lot more than you would expect. So you're going to need to know these. Now I'm not a big fan of memorizing things like this, but what you really should memorize is the special triangle itself. So if I ignore what I have written above there and I were to redo this as a triangle, I know that 45 degrees is one of the special angles. And so the way that appears in a triangle, a right angle triangle, would be, of course, 45 degrees and 45 degrees. And then I remember this, well, the way I remember it, the way I was taught it myself, I remember this as the 1, 1, root 2 triangle. And then from that, I can reproduce any of these relationships. Some people know this triangle as the, so you might see it referenced more using the numbers we have here. Sometimes it can be referenced as the root 2, and 2 triangle. And that's also fine. Both of those are correct and valid. Both of them give the same trigonometric ratios. So there's our summary. The 45, 45, 90 triangle, which is sometimes also called the 1, 1, root 2 triangle. Sine 45 degrees is root 2 over 2. Cos 45 degrees and tan 45 degrees. When it comes to these rationalized values, it's really only important if this is your final answer. Okay? So you want your final answer to be a rationalized number. But for an intermediate calculation, 1 over root 2 is perfectly fine. Okay, let's perform the same exercise. This time we're going to start with an equilateral triangle. Now, equilateral, most people remember the definition of equilateral that all the sides are equal. But a consequence of that, if it's an equilateral triangle, is that all the angles must also be equal. And so an equilateral triangle adds up to 180, which means it has to have 60 degrees in each of the corners or each of the vertices. Now, what if as I did before, I'm going to cut my triangle or I'm going to cut my shape in half. Before it was a square, now it's a triangle. Well, what's the effect of this? Well, if I cut this in half, I end up with a right angle here. This side must be equal to this side, and since they started off as 2, those sides must now be equal to 1. And this angle must be equal to this angle, and since they started off as 60 in total, each one of them must be equal to 30. So, as we did before, let's focus only on one of those triangles. So I've chosen the one on the left side. So as I just noted, half of that angle would be 30 degrees. If this is 30, and actually, sorry, this side length is 1, this side length was 2, so that's the information that carried over from the previous diagram. If this is 30 degrees and this is 90 degrees, that means this one has to be 60 degrees. And then we've got this side, and since it's a vertical side, I'm going to go ahead and use the use the variable y for that. That represents the, well, actually, you know what? I'm not going to label it. The opposite. It doesn't necessarily mean the opposite. It depends on which angle we're talking about. So it's the opposite to 60, but it is the adjacent to 30. And we're going to look at each of those angles. So since I mentioned 60 first, what is the sine of 60 degrees? Oh, before I do that, I guess I better figure out what y is equal to. So what's the relationship for y? The hypotenuse squared, which is 2 squared, is equal to y squared plus 1 squared. So that gives me 4 equals y squared plus 1. Y squared, of course, then would be equal to 3. Y is equal to plus or minus the square root of 3, but y is also a distance, so y must be greater than 0. So we end up with y equals the square root of 3. Okay, now I can get into the trigonometry of these things. I was a little too anxious before. What is the sine of 60 degrees? It's opposite over hypotenuse. Y is the opposite value, so that's going to be root 3 over 2. This is already rationalized, so there's nothing more I need to do about that. The cosine of 60 degrees is equal to adjacent over hypotenuse. That's 1 over 2. And the tan of 60 degrees is equal to opposite over adjacent. So this is equal to root 3. Opposite over adjacent, that's going to be root 3 divided by 1, which of course is just equal to square root of 3. Now, what about 30 degrees? What is the sine of 30 degrees? Well, for 30 degrees, what's the opposite side? The opposite side is 1 over the hypotenuse is 2, so we end up with 1/2. The cosine of 30 degrees is equal to adjacent, but in the case of 30 degrees, the adjacent side is root 3. So that's going to be root 3 divided by 2. And then we have the tan of 30 degrees. And for the tan of 30 degrees, it's opposite over adjacent, which is going to be 1 over root 3, which, if it's a final answer, we really should rationalize. So I'm going to rationalize that, multiplying by root 3 over root 3. And I end up with 1 times root 3, of course, is root 3. Root 3 times root 3 is root 9, which is just equal to 3. Something else you might have observed as I was writing this is that the sine of 30 degrees is equal to the cosine of 60 degrees. And the cosine of 30 degrees is the same as the sine of 60 degrees. And what's the relationship here? Cosine of 60 degrees, sine of 30 degrees, these two things add up to 90. Cosine of 30 degrees, sine of 60 degrees, these two things add up to 90. So this is a complementary relationship between sine and cosine. So if I have any, and for now I'm going to talk about acute angles. So if I had the sine of 5 degrees, that would be the same as the cosine of 85 degrees, for example. And I believe we've touched on this in a previous lesson as well. So here is the nicely formatted summary of the 30-60-90 triangle, which is also the 1, 2, root 3 is another way to remember it, to help you remember the side lengths. But remember where we got this from. This thing came from an equilateral triangle with side lengths of 2. If you did it with side lengths of 1, it would still work. These ratios would still be valid. You would just have a little bit more algebra to do to rationalize it, to clean it up. Okay, well, what about right angles? So we've talked about the angles related to 30, 45, and 60 degrees. What about right angles? 0 degrees, 90 degrees, 180 degrees, and 270 degrees. So the way we deal with right angles is we go back to our definitions that the sine of an angle theta is equal to y over r. The cosine of an angle theta is equal to x over r. And the tangent of the angle theta is y over x. My stylus is having a hard time that close to the edge of the screen. Okay. All right, so now what do I mean by y over r and this sort of thing? What we're going to do is we're going to choose a point. Okay, so we'll choose a point which has coordinates x, y on a thing called the unit circle. Now, this is a fancy sounding term, but all that means is that the radius is equal to 1. It is the unit circle. The radius is 1. So what would that look like? Let's go ahead and do this with a shape. Well, it doesn't look like do I have shapes easily available here? Here we go, shapes, a circle. So let's just put on a circle there. I am assuming that this circle is a radius of 1. So this I can label the radius of this circle is equal to 1. If the radius of this circle is equal to 1, what I'm going to be interested in are the points at these angles, 0, 90, 180, 270, and then this is all the way back around to 360. So let's label those points. If this radius is 1, that means the length along the x-axis here would be 1. So this would be the point 1, 0. Over here, the x-coordinate in this case would be 0, with the y-coordinate would be 1. So that's when the circle is just, or the radius is just this vertical line. Now over here, I have the point, this would have a negative 1 for the x-coordinate and 0 for the y-coordinate. And down here at 270, I would have 0 for the x-coordinate and negative 1 for the y-coordinate. So now that I have those, and this I'm starting with something that's fairly easy to reconstruct as someone who's new to this. So the important part you have to remember here is that it's the unit circle. So from here, I can now actually make some statements about sine, cosine, and tangent. So for example, the sine of 0 degrees, sine is the y-coordinate divided by r. The y-coordinate in this case is 0, divided by r is 1, so the sine of 0 degrees is 0. The cosine of 0 degrees is going to be the x-coordinate divided by r. That is, the x-coordinate would be 1, divided by r is 1, so we end up with 1 there. And then tangent of 0 degrees is equal to the y-coordinate divided by the x-coordinate. That is 0 divided by 1, which is equal to 0. I can do the same thing for 90 degrees. The sine of 90 degrees is y over r. What's the y-coordinate here? It's 1 divided by 1, which is going to be equal to 1. The cosine of 90 degrees is x over r. The x-coordinate here, 0, divided by 1 is 0. Now here's our first very interesting result. The tangent of 90 degrees, tangent is y over x. That would be 1 over 0. So that would be undefined. The sine of 180 degrees is y over r. So that's going to have a y-coordinate of 0 divided by 1, which is 0. The cosine of 180 degrees is x over r. The x-coordinate here is negative 1, divided by 1 is just negative 1. And the tangent of 180 degrees is the y-coordinate divided by the x-coordinate. That is 0 divided by negative 1, is equal to 0. And finally, the sine of 270 degrees is equal to the y-coordinate divided by r. Negative 1 divided by 1 is negative 1. The cosine of 270 degrees is the x-coordinate divided by r. That's 0 divided by 1 is 0. And the tangent of 270 degrees is going to be the y-coordinate divided by the x-coordinate, negative 1 divided by 0. Once again, we end up with undefined. Okay. Now, there's one last thing that I'd like to point out about this. Take a look at the points that I put on the unit circle, and in particular, let's not focus so much on tangent right now, but let's focus on just sine and cosine. The sine of 0 was equal to 0, and the cosine of 0 was equal to 1. This was the cosine of 0 equal to 1. This was the sine of 0 equal to 0. Now, what about the sine of 90 degrees? Sine of 90 degrees was equal to 1. That's the y-coordinate, sine 90 degrees. Cosine of 90 degrees was equal to 0. That's the x-coordinate. And how do I remember x and y? Well, that's the definitions. Remember, the definitions use the x and y. So it turns out sine of 180 degrees is going to match up with the y-coordinate. Sine of 180 degrees. And the cosine is going to match up with the x-coordinate, and so on. In general, on the unit circle, okay, the point which is at xy is the same as if you labeled that point. The x-coordinate is the same as the cosine of the angle. The y-coordinate is the same as the sine of the angle. And this relationship goes further than just these exact values we're talking about, but this relationship is the first place that actually really illustrates where this relationship starts to come from. Okay, so now evaluate using exact values and then express your answer in a reduced form if that's appropriate. So some examples. The sine of 45 degrees, if we, and it's never a bad idea. So with things like this, when I'm explaining them to students, this is the 1 root 2, 45 degrees, 45 degrees. I draw these not because I necessarily need them, but to encourage students to show them it doesn't take long to draw this. Every time you do this, you should be redrawing it until it gets to the point where it's second nature. So since I needed 45 degrees, here's 45 degrees. The sine of 45 degrees is 1 over root 2, which is in a rationalized form, root 2 over 2. And that's it. There's my final answer. The cosine squared of 60 degrees. Well, first of all, that tells me I need the 60-degree angle, which is this one. This is the 1, 2, root 3 triangle. Now, how do you remember the order of those sides? Well, the 1 goes across from the 30 degrees because it's the smallest side. 2 is actually bigger than the square root of 3. And if you're not sure about that, if that doesn't jump out at you, imagine if I squared all these numbers. Well, 2 squared is 4, root 3 squared is 3. So if the square of 2 is bigger than the square of root 3, then 2 itself must be bigger than root 3, at least for numbers bigger than 1. So now I've got my diagram here. I'm just going to remind you that this is the same as the cosine of 60 degrees all squared. You don't have to write that. I'm just pointing out that cos squared, that's actually has this equivalent meaning. What is the cosine of 60 degrees? The cosine of 60 degrees is a half all squared, which in this case is just equal to a quarter. Notice exact values, no calculators. For cosine 45 degrees plus sine 30 degrees, I can actually make use of the diagrams I've already done here. Cosine of 45 degrees, let's use our already simplified form, which is root 2 over 2, or rationalized form. The sine of 30 degrees, here's 30 degrees, the sine of 30 degrees is 1/2. And so common denominator is 2. I end up with root 2 plus 1 over 2. And there is a convention which you normally write it this way. You normally write your radicals second. So that's a communication thing. And it's not one, I would never deduct any marks for that. But that's actually the more common way to see that written. And then finally, 2 tan 60 degrees. So 2, and what is the tan of 60 degrees, which I've put in that bracket? Minus 3 tan 30 degrees, which I put in that bracket. So the tan of 60 degrees is opposite over adjacent. That's root 3 over 1. The tan of 30 degrees is opposite over adjacent, but of course the opposite and adjacent are in different locations now. That's 1 over root 3. So that's equal to, well, this is just 2 root 3 over 1. So I don't write that. Minus 3 over root 3. I'm going to rationalize this. So I'm going to multiply by root 3 over root 3. So I end up with 2 root 3 minus 3 root 3 over 3. So we end up with an interesting result there, because now the 3's divide out. I end up with 2 root 3 minus root 3. But of course, this minus root 3 really just means minus 1 root 3. So I've got 2 of them minus 1 of them gives me just 1 of them. And my answer to this is actually just root 3. Okay, now what about some of these other ones? You might wonder, well, what can we do with this? The sine of 315 degrees. We can make use of some of our previous work. The sine of 315 degrees, where is that going to be? 315 degrees is over here in quadrant 4. 315 degrees looks like this. What would the related acute angle be for 315 degrees? That would be here. The related acute angle in this case would be equal to 45 degrees. So now I can make use of what I know about the cast rule. So in quadrant 4, is sine going to be positive or negative? And the answer is it's going to be negative. So the sine of 315 degrees is exactly the same as the sine of 45 degrees, except for the fact that cast rule tells me this part must be negative. So the cast rule tells me that. And then this is just my RAA. But now I've got 45 degrees. So that's negative, but what is the sine of 45 degrees? It is root 2 over 2. So I end up with negative root 2 over 2 as my final exact answer. The tan of 300 degrees. This one is also in quadrant 4. Here is 300 degrees. So what's the related acute angle in this case? That would be 60 degrees. The tan of 300 degrees is the same as the tan of 60 degrees, but we can't forget to make use of cast here. And cosine's positive in quadrant 4, which means tan is going to be negative in quadrant 4. So now we get negative, and what is the tan of 60 degrees? So never a bad idea. 1, 2, root 3. 60 degrees is this one. The tan of 60 degrees is root 3 over 1. And so my answer ends up being negative square root of 3. cosine of 180 degrees. The cosine of 180 degrees, now this is one that's on the unit circle because 180 is right here, 180 degrees. So what are the coordinates of that point? That point has an x coordinate of 0 and a y coordinate of -1. The cosine matches the x coordinate of the point. So this is, we go straight to our answer here. The cosine of 180 degrees is 0. If you need to, you could have taken an extra step. So you could have remembered that the cosine is the x coordinate divided by the r value. The x coordinate is 0, the r value is 1, but you still end up with a value of 0. The tan of 270 degrees. Okay, I just screwed that up. My apologies. I'm almost done the video, so unfortunately I have to live with this mistake and actually just erase it. So, cosine of 180 degrees, because I can make some pretty big mistakes at times, there is 180 degrees. I hope not too many of you were screaming at the screen that I'm an idiot. Everybody's an idiot at some point in time. Your goal in life is to be an idiot as little as possible. So 180 degrees, what are the coordinates of that point? Let's try this again. The coordinates of that point has an x coordinate of -1 and a y coordinate of 0. So you could remember that cosine is defined as x over r. The x coordinate in this case is -1, the y coordinate is 1, and you get an answer of -1, or you could have just used the fact that the x coordinate is the cosine of theta and the y coordinate is the sine of theta. Now let's see if I can finish off this note without any more blunders. 270 degrees is down here, which I mistakenly labeled as 180 before. So the tangent of 270 is once again making use of the worst circle I've ever seen. Let's try that again. And here is my point. My point has an x coordinate of 0 and a y coordinate of -1. So the tangent is the y coordinate divided by the x coordinate. The y coordinate is -1, the x coordinate is 0, so the tangent of 270 degrees is undefined. Now if you put these values into your calculator, you would get these same answers, but most calculators are not going to give you these exact values, and once we start working the other way as we continue with this, hopefully at least some of you will see the value in knowing how to do it this way. Particularly, if nothing else, if I take your calculators away for a test or part of a test, you'll hopefully see the value very quickly. Okay, so that's it for this lesson. Nothing algebraically difficult, but definitely some things for you to think about there.